In this lecture, I would like to show you how to derive the following result in mathematics. In particular, 1 over pi integral from 0 to pi of cosine to the power k of omega t plus phi, where omega and phi are just two constants. Phi is the phase of the sinusoid and omega is the frequency, the angular frequency. dt equal to k, choose k over 2, and then here we have 1 over 2 to the power k, and let me say that k is an even integer, so let me write k is even, and it is also an integer. Let me also say that omega is related to the period of the function, which is 2 pi times s, and s here is just an integer, and then we divide by capital T, which is the period of the function. In this case, I have chosen capital T equal to pi, so this would be equal to 2 times s in that formula there. If I want to be more general, I would simply have to replace this pi by capital T and also this pi here by capital T. But I'm not going to do it, so we will find that the relation omega equal to 2s will have to be satisfied, but we will find that later. Now I will do it. I will prove this kind of relationship in quite an unusual way. So I will resort to Fourier analysis, and I have never encountered this kind of derivation in textbooks, so it is original. At least I have never seen it anywhere, which doesn't want to stress the fact that I am knowledgeable or that I want to show off, but it is simply something that I deem relevant and I deem interesting because I also use this in my PhD dissertation. So, okay, now this is just an integral and you will find some mathematical derivation, but this is actually quite useful. This kind of formula turned out to be useful for me to derive some other results. I don't know if I have the time in the future to show the results, but never mind. In this lecture, I'm just going to focus on this kind of integral. So let's start from the following formula. X of t equal to, and now we are going to expand this in a Fourier series, and in particular, we have to think that the series will be truncated, but I don't care about the number of harmonics. So you can also think of an infinite number of harmonics in this kind of derivation. It is not so important. But anyway, let me write like this. Summation over n. And then we have a sub n cosine of omega sub n t plus phi sub n. So we have some number of harmonics which added to each other will give a function x of t. In general, this can be a very general function. And then here, in general, I could also write plus a0 over 2. So if there is some kind of mean value for the function, then we also have this term, and it is convenient to write it in this form. There is another way in which we can write the Fourier series, in particular the complex way. So by complex, I mean by using complex numbers. So summation over n, c sub n, e to the I, omega sub n t, and omega sub n is equal to 2 pi n divided by t, which is thought to be the period of the function x of t. So if the function x of t is not periodic, then you can think of t as approaching infinity. But let's think of x as a periodic function, just for simplicity. Okay, so this is the starting point. Now here, there is the relationship between these coefficients and a sub n and phi sub n. So it's not complicated to derive this relationship. C sub n is equal to a sub n over 2 e to the I phi sub n. So if you substitute this expression there and you consider only the real part of that, you will obtain this expression. So if you add all these things up, this is what you will get, even if you don't consider the real part. But it will be easier if you extract from the very beginning the real part, and what you will get is exactly this, because a sub n is also equal to a sub minus n, So in this case, we have to be a little bit careful because here we are summing over negative frequencies, quote unquote negative frequencies as well. So this summation here in general will go from minus infinity to plus infinity. Whereas this summation here in general will go from 1 to infinity. And n equal to 0 is actually this term. So by considering this definition here and also this property and the following property, phi sub minus n equal to minus phi sub n, and if you want phi 0 equal to 0, what you will get is exactly this equality here. So you can see that this expression holds. It's not complicated. Now, what I'm going to calculate is the so-called moment mk. And I will define the moment like this: 1 over t, integral from 0 to t, x of t minus c0, and c0 is just the average of the function x of t, or if you want, this is just a0 over 2 to the power k dt. This is the expression. Now we can use the following formula, this formula here. We substitute it here, and here we get 1 over t, integral from 0 to t, and then here we have a bunch of summations, k summations. So we have to sum over n1, we have to sum over n2, dot dot dot, we have to sum over nk. Now in this case as well, we have to be a little careful because in general we have to subtract this mean value c0 from x of t. So here, over all these summations, we should consider n1 not equal to 0, n2 not equal to 0, dot dot dot, nk not equal to 0. But this is going to make my notation too cumbersome, and it's burdensome to write all these terms, so I'm not going to write these conditions. And it's not really the major point here. But you have to be careful, and you also have to keep in mind that you should remove C0 from all these summations. So all these indices, all these integers could not be equal to 0. So n1 cannot be equal to 0, n2 cannot be equal to 0, and so on and so forth. But I'm going to avoid writing it down, and let's move on. And I'm just going to write one summation symbol, but in general you could also write k summation symbols, and then you get c sub n1, c sub n2, dot dot dot, c sub nk, and then here you have e to the I, and then you have omega n1 plus omega n2 plus dot 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 plus omega nk t dt. Now you can use the definition for omega sub n1, for example, it will be 2 pi n1 over t. Similarly for omega n2 and omega nk, and so on and so forth. And you can rewrite this as summation over n1 dot 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 nk, and then you get c n1, c n2, dot 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 c nk, and then you get 1 over t, integral from 0 to t, e to the I 2 pi over t, and then here you have n1 plus n2 plus dot 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 plus nk dt. Now this integral is actually easy to calculate because if this summation here does not yield 0, then the integral will be an integral of a periodic function, and we are integrating over some period t. So you can easily see that this will yield 0. This integral here will be 0 if this summation is non-zero, because if this summation is 0, then here you will get 1, and therefore the integral will give you t, and t over t will give you 1. So the result here can be written concisely in this fashion. We have to sum, and here we have the following condition to be satisfied: n1 plus n2 plus dot 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 plus nk equal to 0. So we sum only if this condition is satisfied. So we have to sum over n1, n2, n3, and so on and so forth, up to nk, but the summation is performed only if this summation here is satisfied. So for example, let's consider three indices. So we have n1, n2, n3. So if n1 is equal to, say, 4, and 2 is equal to, say, -5, because we have also negative indices. Remember, because the summation is performed from -infinity to +infinity in general, if we have an infinite number of harmonics. And in this case, n3, if we only have 3 harmonics, will have to be equal to -n1 minus n2 in order for the following relationship to be satisfied, n1 plus n2 plus n3 equal to 0. So in this case, it would be equal to -4 plus 5, which is 1, right? So 1 plus 4 minus 5 is 0, and so on and so forth. So you get the idea. If you have k of them, this relation should be satisfied. And then here you have Cn1, Cn2, dot, 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 Cnk. But now we can substitute the equation that we obtained, that I wrote down here. And if you do that, here you get 1 over 2 to the power k summation, and 1 plus n2 plus dot 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 plus nk equal to 0. And here you have a and 1, a and 2, dot 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 a and k. And here you have e to the I phi and 1 plus phi and 2 plus dot 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 plus phi and k, like this. And now you can also simplify this a little bit, because in general the integral should be real, right? Because x of t, I'm thinking of x of t as a real function, so this integral should be real, and we can therefore substitute the real part here. So we can simply consider the real part of this expression, and a and 1, a and 2, a and k are, of course, real quantities, and also phi and 1, phi and 2, phi and k, but we have this imaginary unit, and therefore this is the complex quantity, the complex exponential. So if we consider the real part of that, here we simply have to replace the cosines. So let me do it here in order to be able to do it fast. So I have the cosine of phi and 1 plus phi and 2 plus dot 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 plus phi and k, like this. And this is the formula that I wanted. Now, what I'm going to do is I'm going to consider only one sinusoid. So this is a very general expression which holds for any number of harmonics. But if we only have one harmonic, which means that the function x of t has the following form, a cosine of omega t plus phi, then this expression it will simplify quite a lot. And in particular, in this case, the number n1, n2, ni in general can only take two values, plus or minus an integer that I will call s. So this integer s will be related to the frequency omega. So omega will be 2 pi s over t. And since we only have one frequency, s will only have one value, will only take one value. But of course, the summation here considers both positive and negative integer values for n1, n2, and k. So ni in this case can only take two values, plus or minus s. And since we have this formula here, well, this formula will be satisfied only if k over 2 of these indices are equal to minus s, and k over 2 of those terms are equal to plus s, because the summation should be equal to 0. So that's the only choice. But if k is odd, this cannot happen. What I said just cannot happen, because we cannot find k over 2 positive indices and k over 2 negative indices. So the k over 2 where the indices are equal to minus s, and k over 2 where the indices are equal to plus s. This cannot happen if k is odd, which means that this condition is never satisfied, and basically it means that this complicated expression will be 0. It will be 0 if k is odd. And this equality holds only if we have one sinusoid. one harmonic, because in general it will not hold if we have multiple harmonics. Anyway, now we can simplify this formula here in this case, and in particular this will be equal to 1 over 2 to the power k, and then we have the product of these quantities, which will be equal to a to the power k. So this will all be equal to each other, and we have a to the power k, and then the cosine will be equal to 1, because phi, so we know that this condition is satisfied, and phi sub n1 will be equal to phi sub s, for example, because n1 is equal to s, and k of them, k over 2 of them are equal to phi sub s, and then we get plus k over 2 phi sub minus s, but we know the properties of phi sub minus s, so this is k over 2 phi sub s minus k over 2 phi sub s, so this will be 0, which means that we have to calculate the cosine of 0, and therefore we multiply this by 1. And then we have to multiply this by all the possible combinations, because we can choose several indices. Let's say we have different choices, because we have to choose k over 2 indices, but we have different combinations. We have different choices that we can make. And in particular, the number of choices that we can make is given by k, choose k over 2. It's exactly this formula. And this is equal to 1 over t integral from 0 to t of x of t minus c0, but in this case c0 is equal to 0 because it is the average of the function, which is 0 in this case if it is just a sinusoid. And here we have a to the power k cosine to the power k omega t plus phi dt. So we can cancel a to the power k from both sides. Remember the relationship between omega and t. Omega is equal to 2 pi s over capital T. Now if we choose the period t to be equal to pi, then omega should be of the following form, 2 times s. And therefore here we have 1 over pi integral from 0 to pi cosine to the power k of 2s t plus phi dt. So we can rewrite the formula like this, and we have proved that this is indeed equal to 1 over 2 to the k, choose k over 2, and k, remember that k is an even number, an even integer. So this is the formula that we proved.